Hello everyone and welcome back to Learning Hub. In this video, we are going to talk about a specific type of neural network called the recurrent neural network. So, what exactly are recurrent neural networks? So, in brief, recurrent neural networks or RNNs are a specialized type of neural network designed specifically to handle sequential data, where the order of information truly matters. So, you can think of them as the neural network with a short-term memory. So, unlike a standard or feed-forward neural network, which processes each piece of data independently, like looking at a series of flashcards one by one, an RNN or recurrent neural network is built to understand context. It retains information from previous steps in the sequence and uses that information to influence its processing of the current step. So, this makes the recurrent neural network ideal for tasks like predicting the next word in a sentence, or translating languages, or maybe forecasting stock prices, where the outcome depends heavily on what came before. So how does an RNN work? So the diagram you see is called the unfolded representation of recurrent neural networks, which shows what exactly happens over time as the network processes a sequence of inputs, let's say x0, x1, x2 and so on. So, here is a simple step-by-step breakdown of the process referencing the unfolded diagram. First of all, we consider the input sequence. The input sequence are the data that has an order, like a sentence. We will take an example of the sentence, the dog ran. So, the sentence, the dog ran, is broken down into a sequence of individual inputs. x0 will refer to the, x1 will refer to dog, and x2 will refer to ran. So, first of all, processing at time t equal to 0. The first input x0 or the word the enters the network. It passes into the hidden layer that you see here. This layer processes the input and produces an output h0, which is the hidden state, which is essentially the network's internal summary or memory of x0. This hidden state s0 is then used to calculate an optional output y0 for this specific time step. Then the recurrence or the memory step. So, when the network moves to the next time step, that is t equal to 1, it receives new input, which is x1 or the word dog. However, it doesn't just use x1. It also takes the previous hidden state, which is h0, and feeds it back into the hidden layer along with new input x1. So, this is the recurrent part here, which means the network is constantly cycling information from the past back into the present. Finally, processing at time t equals to 1, which we refer to as contextual understanding. So, the hidden layer now processes both the current input x1 and the past context h0. This combined information creates a new updated hidden state h1, which is the network summary or the sequence to this point, which means basically the phrase the dog. Now this h1 then calculates the output y1, and then this process repeats for every element in the sequence. So at time t equals to 2, the network receives x2, which is the word ran, and combines it with the previous hidden state h1 to create a new hidden state h2 and then the output y2. Although recurrent neural networks have their innovative memory mechanism, they face these three main challenges that can make them difficult to train and deploy effectively for long-term dependencies. The first is slow computation for long sequences. The core challenges here is that an RNN must process a sequence step by step, and that too in order. So to calculate the output or hidden state at maybe time step 50, the network must first have the completed calculations for time step 1 through 49. This means the calculations are inherently serial. They can't be performed simultaneously in parallel. This serial dependencies slows down the training process significantly, especially when compared to other network architectures that can process all input at once using powerful modern GPUs. For a sentence with maybe thousands of words or a time series with thousands of entries, this sequential requirement makes RNNs computationally expensive and slow. The second problem is the vanishing and exploding gradient problem. This is the most critical issue in training traditional RNNs. It occurs during the backpropagation phase, which is when the network calculates how much each weight contributed to the final error, so it can adjust those weights basically in the training process. So if you look at this image here, the image will illustrate the core mathematical reason for it. And the first reason is the chain rule. So to find the effect of a weight in an early time step on the final error, the network has to multiply many small derivative values together using the chain rule. For example, if you see here, dg by dx equals to dg by dy into dy by df, and maybe we can have one more term into df by dz, or sorry, df by dx. So the problem in recurrent neural network is because the parameters or weights are shared across every time step and the network is unfolded across a long sequence, the gradient must be passed back through potentially hundreds of layers. This leads to a chain of multiplication of these derivatives. So if the derivative value being multiplied together are very small, maybe less than 1, like 0.5 into 0.5 into 0.5 and so on, the final product quickly becomes extremely small number, which is almost close to 0. And then a very small gradient means the weight update is negligible or it vanishes. The weights in the initial layers or early time steps are barely adjusted, leading to a very slow learning or a complete inability to learn dependencies from the beginning of the sequence. Conversely, if the derivative values are too large, example maybe greater than 1, their multiplication results in a massive exploding number. So that causes massive weight updates during training, leading to instability. And then the weight becomes so large that they often result in not a number or NAN errors, effectively destroying the network's ability to learn. And then the third problem is difficulty in accessing information from long ago, which means short-term memory. So this particular problem is a direct consequences of the vanishing gradient issue and how the single hidden state carries the memory. Recall that the hidden state at any time step, we'll call it HT, must capture the useful information from all previous time steps. We'll consider a very long sequence like a 50-word sentence. The network's task might be to determine the final word based on the first word. We'll take this particular example here. The man who lived in a massive, sprawling Victorian house next to a park and often walked his poodle was and then 49 words later, baker. So to correctly predict baker, the final hidden state, which is S49, needs to retain the critical information that the subject was the man. Because the information from the first word must pass through 48 layers of multiplication by the hidden state update, the small useful signal from that first word often fades away or is completely overwritten by the constant stream of new and more recent information. So essentially, the hidden state has a very limited short-term memory. It becomes great at linking words that are close together. For example, in the sentence, the dog ran, but fails when it needs to connect information across a significant length in the sequence. This inability to capture long-term dependencies is the primary weakness of the standard RNN architectures, which gave rise to some new recurrent neural architectures like LSTM, GRU, or even the transformer architecture. So I hope the concept is clear to you. I tried explaining recurrent neural network, how it works, and basically its limitation in a very precise and explainable way. If you still have any confusion, do comment down below and I will try to help you out. And in the next video, we will see how we can overcome this particular limitation using transformer architecture. So until then, stay tuned and I will see you in the next video.